Hello, sixth grade students, and welcome to the first week of the energy unit. During this week, we're going to give kind of like the introduction to energy, and what you're supposed to be doing with energy this week is more focused on forms of energy and energy conversions. How does energy change whenever it's converted from one type of energy to another? So here we go. What we're going to use is the worksheets that are stapled as a little booklet in your notebook. Each teacher should have stapled these little booklets into your notebook or told you where they wanted you to have it. Some students have it stapled into the very front cover. Basically, it looks like this. What do you think all those blanks are for? All of those blanks are for you to fill in. We call this the fill in the blank book. It also becomes your study guide for Friday's quiz. I want everyone to look ahead to page 4, right where you see this car. That's about where we'll end today. So we're going to do about 3.5 pages in our booklet, and your job is to stop, to pay attention, and every time there's an underlined word, it will be highlighted in the Smartboard presentation in yellow. When you see yellow, you start writing. When you see yellow, you start writing. The second it comes on the screen, you make sure that you write it. And sometimes during the Smartboard presentation, we might have words, see how it says the transfer of blank energy, that is, you'd have to sometimes go below the picture to find the rest of it. See, this is where it says associated with the blank of the particles of a substance. So this will look a little bit different than what you see on the screen. So you just have to pay attention and follow along, and we will try to help you as best we can. So if you see something in yellow, you write it down, all right? Okay, so now I am going to show you the Smartboard presentation. So basically this is how it goes. I see yellow, don't you? I see the word forms, heat energy, thermal, and motion. So you need to go to your sheet and open it up, and while the teacher's talking, which is me, you need to fill in what you see. When the teacher is talking, who is me, you need to fill in yellow what you see. I see forms, I see heat energy, I see thermal, and I see motion. So let's begin. Conservation of energy. Energy can be in many different forms. Students should know sources and properties of the following forms of energy. Heat energy. Heat energy is the transfer of thermal. Thermal. Therm in English class means heat. Therm means heat. When we talk about a thermos that you put into your lunchbox, it keeps things hot, like soup. So a thermos keeps things hot. Heat energy, heat means hot, or lack of heat means cold. So heat means transfer of thermal energy, that's energy associated with the motion of particles of a substance. So the faster that particles are moving, the more heat energy or thermal energy they have. So sometimes people say thermal instead of heat. Heat is called thermal. There's a song that each student will be learning that is called the Forms of Energy song, and it goes to the tune of Frosty the Snowman. Forms of energy, there are many you should know. Well, when you go further into the song, it says heat is called thermal. During that part, you need to remember the heat and thermal energy are the same thing. But that's just the energy associated with motion of particles of a substance. So what exactly does that mean? You have 3 little boxes that have little dots around them. And I want you to fill in these 3 boxes with the 3 states of matter. And you'll understand heat energy and it being associated with the motion of particles by doing this activity. The first box I want you to write water in liquid form. So all of these boxes are going to be water. But your first box, I want you to draw what you see. These are the molecules inside water, liquid water. When water is just sitting in a cup in liquid form at about this temperature, which we're not really going to worry too much. It's saying 20 degrees. This would be Celsius. At 20 degrees Celsius, the molecules just look like this. So why don't you just try to draw the molecules kind of close together, but just kind of here and there, kind of jumbled together. Do it really quick. Jot it down as fast as you can. Write that the temperature's 20 and that this is in liquid form. So right here you should have written state of matter, liquid. Temperature should have been 20 degrees Celsius. You could have just put a C. And the particle motion, you could just say moving kind of medium, medium motion, not real fast, not real slow. And in the next box and the next box, I'll tell you what to write in a minute. All right, so that was water. Now I want you to keep your eyes really close right here as I show you what happens when we turn up the heat. Look at how the bubbles are starting to, just like if you're cooking water on the stove, getting ready to boil it to make some soup or something. Just watch what happens when you turn the heat up really, really high. Look at this, is showing how heat has been added. It's 99 degrees or 99 degrees Celsius here. Now look, it says steam, gas. So I want you to write the state of matter in the next box is gas. The steam has all released out of it. Look at how all the water's gone. So when the temperature was 100 degrees Celsius, 100 degrees Celsius, look at that. I want you to draw all of those molecules. They're going crazy. That motion, the heat that is associated, it says heat energy is a transfer of thermal energy that is associated with the motion of the particles of a substance. They are going nuts. They can't wait to get out of there. So they're all over the place. But now, what happens when we make it cold? Let's find out. Down, 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 down. Brrr. Starting to get cold up in here, man. I'm starting to get very, very chilly. Do you see how all these little ice crystals are starting to show? Oh, I'm getting cold, man. We got to get together. Ah. So what happened? Once it's turned into ice, which you should write ice, it's a solid. Once it's turned into ice, all of the molecules line up like little soldiers, and then it looks like it's even shaped like an ice cube. So at -1 degree Celsius, this is what happens. And there we go. Quickly get that taken down. So ice is a solid, -1 degrees, and then draw your little blocks, which are just circular molecules. Remember that all matter is made up of particles that are too small to be seen. That was something that you were taught in the 5th grade. As heat energy is added to a substance, the temperature goes up, indicating that the particles are moving faster. The faster the particles move, the higher the temperature gets. Now, examples of heat energy. So all of the examples that you should know of heat energy are materials like wood, candle wax that's burning. So if I burn wood, if I burn candle wax, the sun is an example, and electricity are all examples of heat energy. So if I ask you that on a quiz, you need to know it. Solar energy is the energy from the sun. Solar starts with an S. Sun starts with an S. Sounds pretty easy to me. Solar energy is the energy from the sun, which provides heat and light energy for Earth. Solar cells can be used to convert solar energy to electrical energy. Solar cells can be used to convert solar energy to electrical energy. Here's a solar cell in a calculator. That's what that is right there. We love solar calculators. I can remember when I was a little girl and they first came out. I told you I was old. Green plants use solar energy during photosynthesis to produce sugar, which contains stored chemical energy. Green plants use solar energy during photosynthesis. Well, we know that. Photosynthesis makes food only in the sunlight. See, you need the sunlight to make food. That's solar energy. Most of the energy that we use on Earth originally came from the sun. Make sure that you get these. Solar energy is the energy from the sun, which provides heat and light energy for Earth. Solar cells can be used to convert solar energy to electrical energy. Green plants use solar energy during photosynthesis to produce sugar, which contains stored chemical energy. Most of the energy that we use on Earth originally came from the sun. Don't forget, we're checking to see that you have all of these filled out. When you're in little teacher group tomorrow, the first thing the teacher will do is make sure that you have all of these filled out. I will also put this video on Edmodo for you. So just in case you're not the fastest writer in the world, you'll be able to see it on Edmodo. All right, here we go. Chemical energy is energy stored in particles of matter. So chemical energy. I say chemical, you say battery. Chemical. Chemical. I say battery, you say chemical. Battery. Battery. Now you should be chanting after me. And it's okay. The kids in the class are allowed to. The teacher's asking them to. So your teacher can moderate and make sure that you're doing it right. So if I say chemical, you say battery. Chemical. Chemical. I say battery, you say chemical. Battery. Battery. Ah, that's great. But it's also in sugar and food. Chemical energy can be released, for example, in a battery or in sugar or food. So I say sugar, you say chemical. Sugar. Sugar. I say food, you say chemical. Food. Food. I say chemical, you say food. Food. Chemical. Chemical. Food. Battery. Chemical. All of these have to do with each other. Chemical energy is in a battery and it's in sugar and food. So if you remember that a battery, just remember these pictures. Remember chemical energy. If you bit into a battery, ugh, you would taste a chemical and you'd probably get very sick and possibly even die. I would never want you to bite into a battery. When you bite into food, it's filled with sugar. We've learned how that was happening when a plant makes food. It's photosynthesis. Let's look at that reaction one more time. Remember in our photosynthesis preparation station, we had Phil mixing up a birthday cake. He put energy from the sun, carbon dioxide, and water into a bowl, and he whipped it. He whipped it good, and he made what did he make? What did he make? A sugar cake. What did he make? A sugar cake. What did he make? A sugar cake. Sugar and oxygen stay together because they're BFFs. So what? Don't forget that. That's really important. You've got to keep it fresh in your memory. Electrical energy is energy flowing in an electric circuit. Electrical energy, electric circuit. They both start with an E. That sounds like a no-brainer to me. That means it shouldn't be very hard to remember. Electrical energy, electric circuit. Sources of electrical energy include stored chemical energy in batteries, solar energy in solar cells, fuels or hydroelectric energy in generators. So sources of electrical energy include stored chemical energy in a battery, solar energy in a solar cell, fuels or hydroelectric energy in generators. Mechanical energy is the energy due to a motion and position of an object. We call the motion kinetic energy. So it's kinetic mechanical energy. Mechanical energy is broken up into two pieces. One part is called kinetic, which is energy due to the motion. So I think kinetic, you think motion. I think kinetic, you think motion. I think kinetic, you think motion. Kinetic, motion, kinetic, motion. And position, which is potential. Position starts with a P, potential starts with a P. So if something's just sitting and it has the potential to do something, that is considered the position of an object. So mechanical energy is energy due to an object's motion and position of an object. When objects are set in motion, they are in position where they can be set in motion, they have mechanical energy. Let's look right here at this roller coaster. So where it's blue, it's saying it has potential energy. Where it's green, it's saying it has kinetic energy. And basically, if you were going up the roller coaster, you would be in motion. So what did I say motion was? Motion is kinetic. So moving up, you would be kinetic energy. When you got to the top and you're just sitting still in position, P for position, P for potential, right up at the top before you start to go down, you'd have potential energy. And then going down, that would have been kinetic. And now you're at the bottom, potential. Now you're going up, kinetic. Now you're at the top, potential. Now you're going down, kinetic. Now you're at the bottom, potential. Now you're going up, kinetic. You're upside down at the top, potential. Now you're swirling down, kinetic. Do you understand that potential and kinetic energy are always changing due to the motion and position of an object? Mechanical energy is any energy involved with motion or position. I want you to stand up at your chair, and I am going to have you show potential and kinetic energy. When I say go, you start running. In place, when I say freeze, you've got to stop. Mark, set, go. Run, 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 freeze. Do it again. Run, 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 run. You're showing kinetic energy. Run, 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 run. Kinetic, 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 kinetic. Freeze. You're showing potential energy. So kinetic energy is energy of motion. Potential energy is when you freeze. You have the opportunity to move, but you're choosing not to. All right, please have a seat. Mechanical potential energy. Potential energy is a stored energy. So potential energy, when I told you to freeze, you were storing that energy. Mechanical potential energy is related to the position of an object. A stretched rubber band has potential energy. Water behind a dam has potential energy because it can fall down the dam. A stretched rubber band has potential energy because it can be released and show what kind of elastic energy it has. So, mechanical potential energy. It is potential energy that's stored energy. Mechanical potential energy is related to the position of an object. Examples are a stretched rubber band or water behind a dam that has not yet fallen. Mechanical kinetic energy is kinetic energy that is the energy an object has due to its motion. So mechanical kinetic has to do with motion. When we were running in place, that was mechanical kinetic. Mechanical kinetic energy increases as an object moves faster. The faster you ran at your table, the more the mechanical kinetic energy you had. A moving car has kinetic energy. If the car moves faster, it has more kinetic energy. I want you to look at this little tiny picture that you have right here. Look at the little boy swinging on the swing. Which letter represents the most potential energy? Remember, which one represents the one with the most position? Potential means position. Is it when the swing's just sitting still? Or is it when he's way up here high, about to go down? Or is it when he was swinging out in the first place? Which letter represents the most potential energy? You try to write that down. Which letter represents the least potential energy? The one where it's not really, it has the least potential energy. Which letter represents the most kinetic energy? So which one represents the most potential energy? Which one represents the least potential energy? And which one represents the most kinetic energy? Okay, let's see what you guys chose. Well, let me show you. Whenever the swing is just sitting still, like it is in C, that's when it's representing the least potential energy. It has potential to move, but it's not moving in any way, shape, or form yet, so it has the least potential energy, so the second answer right here should be C. Which letter represented the most potential energy? When he's way up here, waiting to fall back down. That's the most potential energy. Which letter represents the most kinetic energy? When he's swinging up. That's kinetic energy, B. So hopefully you got those right. If not, we'll have more practice. All right, this is a activity where I want to show you a little bit of it, and then your teacher can go over the next one or the following ones with you, because there's a couple practice pages here. Potential and kinetic energy practice. The apple hanging from the branch has what kind of energy? Is it kinetic or potential? Remember, kinetic means it's in movement. Potential means it's in position. So an apple hanging from a branch has, yes, position. It has potential energy. Now let's pretend for a minute that we guessed kinetic, which of course we know is wrong. It would say oops. So we know that potential is the right answer, because an apple just hanging from a branch isn't moving at all. The potential energy is what? Motion or stored? Potential energy, is that motion or stored? Good job. Potential energy is stored. Potential energy changes to what kind of energy when the apple starts to fall? Well, if the apple's not moving, it's potential. So what happens when the apple starts to fall? What happened when you ran in place? Good job. It's kinetic. Kinetic energy is energy of motion. Would an apple sitting still on the ground have kinetic energy? Yes or no? Would an apple sitting still on the ground have kinetic energy? Yes or no? Good job. It's sitting still. That's position. Remember, P for potential, P for position. Let's move on. This is some more practice that you can do with your teacher. You can do it a little bit later and see what your teacher says. And here's another one that you can practice with. The law of conservation of energy states that energy cannot be created or destroyed. It may be transformed from one form into another, but the total amount of energy never changes. Energy cannot be created or destroyed. It may be transformed from one form to another, but the total amount of energy never changes. Now, we have a chant for this. I passed out the chant to every teacher. They have a little tiny piece of paper for you. You should tape it into your notebook. And it is a chant that goes like this. Energy can neither be created nor destroyed. What? Energy can neither be created nor destroyed. What? Energy can neither be created nor destroyed. It just changes form. Energy can neither be created nor destroyed. What? Energy can neither be created nor destroyed. What? Energy can neither be created nor destroyed. It just changes form. Now that is the law of conservation of energy. You need to memorize that law. So you might as well just memorize the chant. The chant teaches it to you. If you know the chant, you'll know that energy cannot be created. Nobody can create it. Nobody can create it in a science lab. You can't do some experiment and create energy. Energy always has been. It always will be. No one can destroy it. No one can create it. It just keeps changing from one kind of energy into another kind of energy. For instance, if I take a plug to my overhead projector that makes my smartboard light up, and I plug it in. So that plug is an electrical cord. So that means electrical energy has to go through it. I plug it in, electrical energy starts going through the wire into the little machine, a fan is turned on, a light bulb projects on the screen, and you can hear it make a little noise. So the light bulb projecting means that it was electrical energy changed to light energy. The sound of the motor means electrical energy was changed to sound energy. Watching the motor move means electrical energy was changed to mechanical energy, because mechanical means movement. And there's even other energies that it's transformed into, but that was just to give you an idea. Examples of potential and kinetic mechanical transformations might include this. When water is behind a dam, it has potential energy. That means it has energy of position. The potential energy of the water changes to kinetic energy, the energy of movement of the water as it flows over the dam. So water behind a dam, potential. Water that goes over the dam, kinetic. And that is a dam that is holding back water in order to make electricity. This is a whiteboard activity, and you're supposed to write a K if the answer is kinetic and write a P if the answer is potential. When a rubber band is stretched, kinetic energy is transformed into potential energy. When a stretched rubber band is released, its kinetic energy is transformed into potential energy as the rubber band moves. When a book is lifted to a shelf, it had potential energy that's transferred into kinetic energy. So when a book is lifted to a shelf, potential energy, because it's down on the table, is transformed into kinetic as it's lifted. If a book falls off a shelf, potential energy transforms into kinetic as it falls. So if the book falls off a shelf, the potential energy is transformed to kinetic energy. Okay, these are examples that come straight from the state standards. You need to know these specific examples. Here's the example, a book falling. What kind of energy transformation is it? When a book falls, it's kinetic energy, energy of motion, changing into sound and heat. When water moves over a dam, that's kinetic energy of motion, changing into electrical via a generator. Green plants is solar energy changing into stored chemical energy. When you see this arrow in the energy unit, it means changing into or energy transformation. Respiration, whenever we eat food or plants eat food, it's chemical energy changing to kinetic moving energy. Burning carbon-based fuels. Anytime you say burning a fuel, gasoline, any of that is chemical energy changing into heat energy and electrical energy. Electric circuit using an outlet that you plug into the wall is electrical energy transforming or changing into mechanical energy, heat, sound, and light. We're going to do just about 2 or 3 of these, and then I'm going to let you do the rest of them with your teacher, depending on how much time you have left. Basically, you're going to select the correct form of energy observed in the picture. So this little man is lighting a firecracker. I want you to tell me, what kind of energy is it? We'll know if it's correct because when we pull it to the left, it'll either have a check mark or it won't. So, do you think that it's chemical energy whenever you light a match to light a firecracker? You do? Well, you're right. See how it has a check mark? That means it's chemical energy. Mark that on your paper. What about electrical energy? Is there any electric wires here? If there aren't, then you would not pull that out. See, that's an X. So let's leave that one in. Does it have potential energy? He's lit it. He hasn't lit the firework yet. Sure, it has potential energy. It has energy of position. What about heat? That's a no-brainer. Everybody knows that heat's associated with a match. What about kinetic energy? Energy of motion? Yeah, you better believe it. What about light? Well, you see the match lit, so you know that one's right. What about nuclear power? That's dealing with atoms and splitting atoms and fusion and all that crazy stuff that has to be happening in a big, big laboratory. Nuclear bombs and stuff. I don't think that's him. I don't think he's doing anything with nuclear anything. So if I pulled that one out, it would say no. So we're going to leave that one over. What about sound? Boom! You better believe it. Okay, that's awesome. So now let's look below and see what it says. Explain one energy transformation seen above. Well, I think that he starts out with potential energy and then it changes into light energy when he lights the match, and then it changes into heat energy and sound when it goes boom. So I'm going to put heat and sound together. Awesome! Now you try the next one. I want you to try this one with your teacher, this one, this one, this one, and I'm going to do this one with you because this is our last one for the day. Then all the rest of the time, you and your teacher can go back and you guys can do all the other ones that we skipped. All right, here we go. Look at this. Select answers from the perspective of the man. Not the car, but looking at the man. Does the man have chemical energy? Sure. He had to eat in order to hammer. So he had to have had food inside his belly in order to use that hammer. Whoops. What about electrical energy? Does the man have electrical energy? No. He doesn't have any wires hooked up to him. What about potential energy? Sure, he was in position right before he did this. He's in position to hammer down right now. What about heat energy? Sure, he's putting off heat. He's sweating up a storm trying to hammer into that car. What about kinetic energy? Sure, he's in motion. He's really going to hammer that thing. What about light? Does he have any lights hooked up to him? No, that would not be right. Electrical would not be right. What about nuclear? Is he about to go boom? No, that one wouldn't be right. This one's not right. This one's not right. Electrical's not right. What about sound? Do you think he's going to make some sound whenever he bangs there? Sure will. All right, now look below and explain one energy transformation that we see. Well, I think the man's going to start with potential energy because he's going to have the potential to throw that hammer down. And when the hammer hits, he's changing it into kinetic energy because that's the energy of motion. And it's going to make a lot of heat and a lot of sound. Okay, you should be finishing and filling out the rest of your book, making sure you go back and filling it out, and I will put this on Edmodo for you, and you do the rest of the activities with your teacher. Don't forget, there's a quiz on Friday over everything we've covered. You make sure that in the next 3 days when you're in your blended learning rotation groups that you do all the work, because all of the work was designed to help you get an A on that test or that quiz Friday. So good luck. Don't forget, learn the chant, the Law of Conservation of Energy chant, and learn the Forms of Energy song lyrics. They'll really help you. Thanks and have a great week.